Hi guys, so today's lesson is 5.4.2, which is about solving exponential equations. In the last lesson, 5.4.1, we talked about solving logarithmic equations, so pretty similar. Okay, today for the warm-up, you're going to use properties of logs to condense, meaning make this smaller, make this into one logarithmic expression. So take a look here. You're going to notice because there's a minus sign in between these, and we always double check that they've got the same base. These are both natural log expressions, so they both have base e, which means we can combine them, and this is quotient rule, so we have natural log of 5x plus 2, it's inside this parentheses, divided by the 10x plus 4. And then there is our condensed expression. Okay, so first, before we talk about how to solve exponentials, let's talk about how to find the inverse of an exponential function. These steps are going to look very similar to the steps that we learned for solving or finding the inverse of a logarithmic function. So step number one, always just change f of x into y. We want to make our lives a little bit easier and simpler, so we're going to get rid of the function notation just for the time being. Okay, step number two, this is the same as finding any inverse for any function algebraically. You interchange or you switch the x and the y coordinates, okay? And then step number three, you want to isolate the exponential expression on one side. So because you're going to try to solve for the new y value, you want to isolate that exponential expression on one side. Doesn't matter if it's the left side or the right side of the equation. Step number four, once you've got that exponential expression by itself, so whatever base to the power of, some exponent here, okay, that's what your exponential expression looks like, then you're going to eliminate that base b by taking the log of both sides of that equation using that same base. So whatever base that is, you're going to take the log of that base of both sides, okay, of the equation, and then you've got, some number or some value over here. Step number five, then you solve the exponential equation for your new y value to get the inverse. And finally, just like at the very beginning, we replaced function notation, you're going to go back and replace y with function notation again to denote that it is the inverse, so inverse of f of x, or whatever that original function is called. Okay, so let's go ahead and practice. I've got the steps written out to the side here for us to see as we go through and solve this problem. Okay, so step number one, we're going to change f of x to become y. So we get y equals 5 to the power of 4x plus 1, all of that divided by 2. Okay, step number two, actually, let me just erase this so you can see real fast. I'm going to write this in a different color. Okay, so that's step number one. Step number two, swap the x and the y values. So x equals 5 to the power of 4y, all of that plus 1, all of that divided by 2. Okay, now technically this is our inverse, but we have to then isolate and solve for y. So step number three, we're going to isolate the exponential part. So locate the exponential. Again, the exponential is just some base to the power of an exponent. So this right here is the exponential, 5 to the power of 4y plus 1. So to isolate that, we want to multiply both sides by the 2 to get rid of that on the same side, okay? So 2x equals 5 to the power of 4y plus 1. So now our exponential is isolated. Step number four, we convert it to a log expression. And if we go back here, what we said is we eliminate the base by taking the log of both sides with that same base that we're talking about. So our base here is 5, so what we're going to do is take log base 5 of both sides. So let me find a new color here. Okay, so this is going to become log base 5 of 2x equals log base 5 of this whole thing, 5 to the power of 4y plus 1. All right, and the reason that we do this and we take the log of the same base of that exponential is because this right here, when you have log of some base of that same base, that same number, then that is one of our log properties, and that just becomes 1 or 1 times, whatever that exponent is left with, okay? So then we come over here, we've got log base 5 of 2x equals just the 4y plus 1, because that log base 5 of 5 cancels out. And then step number 5, solve for y, and we replace it with the inverse notation, okay? So now we just have to isolate y, get that by itself, so I just subtract 1 from both sides, so I get log base 5 of 2x, all of that minus 1 equals 4y, and I'm also just going to put the 2x in parentheses so that you know the minus 1 is outside of that. And then last step, I'd have to divide both sides by 4. So I get y equals log base 5 of 2x, all of that minus 1, all of that divided by 4, and then the final step is I need to replace this y with f inverse of x, okay, because our original function was f of x, and since we just found the inverse, I just need to denote that using this notation. Just because it's more specific, it tells us, oh, this is the inverse of function f of x. Okay, so then we're done with that whole thing. So yeah, it's a little bit long, this process sometimes, but if you follow these 5 steps, step by step by step, you will end up at the correct answer at the end, always. Okay, so that's how to find the inverse of an exponential. All right, now let's talk about solving exponential equations by expressing each side as a power of the same base. Okay, so I'll explain what this means in a second, but one of the easiest ways to solve exponential equations is using this method. If we can get each side of the equation to have the same base b, okay, and they're both raised, to some exponent, some power, then we can basically eliminate those bases, because if I have some number to the power of m equals that same number to the power of n, because they're equal, I therefore know that the exponents m and n have to equal each other. And then that allows you to get rid of the bases and just set the exponents equal to each other. So first step is we rewrite the equation in this format where you get the same base. So if you want to write that just, in your brain to keep it straight in your brain. So get the same base. Basically, you rewrite each side to where it has the same base. Then you set m equal to n, so the exponents. In essence, you get rid of the bases. Okay, and then you solve for the variable. So we'll see what this looks like in just a second. All right, let's go through a couple examples here. Okay, first example, we've got 5 to the power of 3x minus 6 equals 125. So the thing that you're going to have to do when you're evaluating whether or not you can solve exponential equations this way is look to see if you can get a common base. So right now I have 5 on the left side and I have 125 on the right side. What I would want to try to look at and see is, can I rewrite these with both of them having bases of 5? Well, if I think about 125, does 5 to the power of something give me 125? Well, yes, 5 to the power of 3 gives me 125. And so that is how I'm going to rewrite this, okay? Because I already know that the left side has a base of 5, and I want the right side to match that, or I want to come up with a base for both of them that matches. So I can rewrite 125 as 5 to the power of 3. So now, this is step number 1. I've gotten both of these to have the same base, okay? Both are base b or base 5. And because of that, 5 to the power of 3x minus 6 equals 5 to the power of 3. Well, I know then the exponents have to be equal to each other. So that's step number 2. We're going to get rid of the bases and just set the exponents equal to each other. So 3x minus 6 equals 3. This only works, however, because these bases are the same. If those bases were not the same, then this would not work, okay? And then step number 3, simple, we just solve for the variable. So I'd add 6 to both sides, I'd get 9, and then I could divide both sides by 3, and I'd get x equals 3. And the nice thing about this, you do not have to check your answers, but the nice thing about this is you can always go back, double check that you did it correctly, plug this in and check. So I could rewrite this and see, okay, or just do this in my mind, 5 to the power of 3 times 3 minus 6. Does this in fact equal 125? Well, this becomes 9 minus 6, and then that becomes 5 to the power of 3, which, yes, in fact, does equal 125. So if you want to do a quick mental check or, just plug it back in, you can always verify that your answer is actually correct. Again, that's not required. However, that sometimes is helpful. Okay. Example number 3. So solve 8 to the power of x plus 2 equals 4 to the power of x minus 3. So if I think of, 8 and 4, can I get a common base here? Well, I can't rewrite 8 as 4 to the power of some number, okay? That's a whole number. So 4 times 2, yeah, that gives me 8, but 4 to the power of 2 is 16, and so that's not going to be it. So sometimes what you have to do is you actually have to rewrite both sides to have a different base. So if I think about 8 and 4, I know that 2 is raised to the power of a whole number to get both of those. So if I raise 2 to the power of 3, that equals 8. And you can kind of write this over to the side if you need to. So 2 to the power of 3 is 8, and 2 to the power of 2 is 4. So if I notice that, I can rewrite these to both have those bases of 2. Okay, so this is 2 to the power of 3 instead of 8, all to the power of x plus 2. Okay, so I'm just quite literally replacing the 8 with 2 to the power of 3. And then this equals 2 to the power of 2. I'm replacing this 4. All to the power of x minus 3. Okay, I know that looks a little bit wonky because of just, the parentheses and then the extra exponents out here, but all I'm doing is I'm replacing those. So now we've got our common bases here. Okay, so then what I can do is I can, again, eliminate the 2's. I can eliminate my common bases and just take what's left of the exponents. But you have to note this is 3 times x plus 2 and 2 times x minus 3, okay? So anytime you've got this, outside of parentheses and that's raised to the power of something else, you're just going to multiply them. So I can rewrite it like so. I got rid of my bases, and then I just solve. So I would need to distribute here. I'd get 3x plus 6, distribute here on the right side, 2x minus 6, and then continue solving. So I would subtract maybe 2x from both sides first to give me x plus 6 equals minus 6. Then subtract 6 from both sides, and I get x equals negative 12. Again, if you wanted to verify, you could just plug this back in up above for both of those. Okay, so example number 2, all we had to do was change one side of the equation to get that common base because it had a common base with 5 already. But in example 3, we actually had to change both sides of the equation to get a common base. So I'd say that's kind of the hardest part of this, and this is where you want to just start thinking about your whole numbers and what those numbers give you when you raise them to the power of, like 1 to the power of 2, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 3 to the power of 2, 3 to the power of 3, 3 to the power of 4, things like that. So try to think of those positive whole numbers, positive integers, and if you raise them to the power of positive whole number exponents, what does that give you? Okay, let's try one more example. So 3 to the power of 2x minus 1 equals 27. So I look, this one's base 3. I try to see, can I rewrite 27 to also have a base of 3, which I can. And if you're trying to think of this, again, think of, 3 to the power of 1 is 3. 3 to the power of 2 is 9. 3 to the power of 3 is 27. So I can rewrite this as 3 to the power of 3. So you can just use a calculator, help yourself out, or just do the mental math. All right, we've got matching bases here, the 3 and the 3. So then I can get rid of those, and I can set the exponents equal to each other. So 2x minus 3 has to equal 3, and then I solve for x. So here I would add 1 to both sides, and then divide both sides by 2, which would give me x equals 2. Okay, now that doesn't always work. So this is probably one of the simplest ways to solve exponential equations. That's why I show you this first. However, there are going to be plenty of times when you cannot find a common base And so instead of doing that, we can also use this other method for solving exponentials, which is using logarithms to solve them. Okay, so if we're going to do this method, first step is we isolate the exponential expression. So again, that's whatever base to the power of exponent. Okay, so we get that by itself on one side of the equation. Then we can, since we're going to use logs to solve this, we can either take the common log of both sides if there's a base of 10, or if it's a base other than 10, we take the natural log. Okay, so we take the natural log of both sides for bases other than 10. All right, then we can simplify using one of these three properties. So we could write, if we take the natural log of both sides, natural log of, our exponential expression, b to the power of x, we can use power property and rewrite this as x times that natural log of b. Or we can use this property if we end up getting natural log of e to the power of x. We know that natural log of e, because they both have the same base, that ends up just canceling out and giving us that exponent x. Or same thing here, if we have common log base 10 of 10 to the power of x, these cancel out and we're just left with x again. Okay, and then we want to solve for the variable. So in this case, up above, all of these are x's. All right, so let's do an example here. We've got 5 to the power of x equals 134. So first thing I would do is I would look and see, can I get a common base? Well, this base 5, since 5 is a prime number, and I'm thinking about does 1 to the power of something give me 5, or 2 to the power of some whole number, or 3 or 4? No, they don't. So I'm not going to rewrite that side. And then 134, unfortunately, I cannot get that to have a base of 5 without using decimals. Okay, so I'm not going to use the first method that we talked about with finding a common base. So I'm going to use this method instead and use logarithms. So first step, we want to isolate the exponential again. So base to the power of exponent, which is the 5 to the power of x. So in this case, that is already isolated. I don't have to move anything else away from it. Step number 2, we take the common or natural log of both sides. So again, if it is a base 10, we're going to take the common logarithm, which just means, actual log of both sides of the equation. If it is a base other than 10, we're going to take the natural log. Okay, so we'll take natural log of 5 to the power of x equals natural log of 134. And if you want to put these in parentheses, you can. So that's step number 2. All right, step number 3, we are going to simplify. And so that is using one of these properties. So if we can cancel anything out, if we've got the same base and then the same number next to it, great. And if not, then we're going to use power property like right here. So we don't have the same base, anything like that. So we're going to just use power property and rewrite this, because the goal is we need to solve for x. And in order to do that, x needs to be out of the position of the exponent. So x times natural log of 5 equals natural log of 134. Okay, so we simplified that. And then step number 4, we want to actually solve for x. So the only thing I have left to do here is I would divide both sides by natural log of 5. So x equals natural log of 134 divided by natural log of 5. And then this you can actually plug into a calculator. That's why we either take the common log or natural log of both sides, because you can plug that into a calculator. Even most iPhones or Androids, you can plug this in. So plug that into your calculator and you get about 3.04. Anytime you are rounding, by the way, I would suggest at a minimum you need to go out to 2 decimal places, so the hundredths place, if not an additional third place, the thousandths place. Okay, so both of those answers are correct. All right, let's practice another example similar to this. So we've got 3 to the power of 2x minus 1 equals 7 to the power of x plus 1. I'm going to quickly just try to evaluate, okay, can I get a common base between the 3 and the 7? Unfortunately, I can't. And with prime numbers like this, it's pretty easy to see. Okay, so next step you're going to do is isolate the exponential. Well, you're going to notice both sides are exponentials. Okay, so this is a base to the power of an exponent, and this is, a different base to another power of another exponent. So they're isolated. They're each on, one side. We can't isolate them any further. So then we're going to take the common or natural log of both sides. Well, these are both bases other than 10, base 3 and base 7. So I'm going to take natural log of both sides. So natural log of 3 to the power of 2x minus 1 equals natural log of 7 to the power of x plus 1. Okay, so that's step number 1. Step number 2. Step number 3, simplify. So again, by simplifying, we mean, can we cancel anything out? And if not, can we use power property to move the exponents out in front so that we can then get the x's to not be in the exponents anymore? So yes, that's what we're going to do. I'm going to move this whole thing out in front. So 2x minus 1, I'm going to put that in parentheses, times natural log of 3 equals this x plus 1 out in front times natural log of 7. Okay, now here we run into a little bit of a trickier scenario just because we've got x's here and here. So normally if we just had x's on one side like we did previously in this example, we would just move everything else away from it to the other side. However, because we've got both of these and I need to get my x terms together, the best way to do this is actually going to be something that seems a little bit counterintuitive, which is to distribute, okay? And so what we're going to do is we're going to, let me just change colors, multiply natural log of 3 times the 2x and times the negative 1. Okay, so we would get 2x times natural log of 3, and then minus 1 times natural log of 3 is just minus 1, or minus natural log of 3, minus 1 times natural log of 3, okay? We're going to distribute that because, again, I need to get my x terms together. So even if I were to divide both sides by this, then I'm going to have an x expression divided by an x expression, and that's not going to be good. So then I'm going to do the same thing over here, distribute, so x times natural log of 7, and then 1 times natural log of 7 is just 1 times natural log of 7, so natural log of 7, okay? So then we add that. Now you'll notice, okay, I've got 2 expressions here. Actually, let me use a different color. 2 expressions that have x's in them, so this one and this one. So I want to get those on the same side together. And then these expressions that don't have x's, I also want to get those on one side together. So I'm going to just subtract this. X times natural log of 7 to the other side. Okay, so I get 2x times natural log of 3 minus x times natural log of 7. And I'm also simultaneously just going to add this natural log of 3 to the other side, if that's okay with you guys. Okay, so that I can get my like terms together. So natural log of 7 plus natural log of 3. Now, I'm going to leave these in this format for now, okay? And then I'll worry about combining more. So I've got my 2 terms on the left side that both have x's. And to get that x isolated, to be able to solve for it, what I'm now going to do is I'm going to factor this out of both of these expressions because I've got an x here and a 2x, so I can factor an x out from both. Okay, so if I factor an x out in front, I'm going to be left with 2 times natural log of 3. Okay, so I'm just moving that x out in front. And then right here, I'm just going to be left with minus natural log of 7. And actually, let me just get rid of these parentheses just so it looks a little less messy. Okay, so then I have x by itself out in front. All I need to do is divide by this entire thing. So 2 natural log of 3 minus natural log of 7. So divide this. And again, I know that this looks messy, and this is one of those more challenging examples, which you'll see similar stuff in your homework. Okay, so I've got this entire fraction here. Okay, and then this is where you would go ahead and plug this into your calculator. Make sure if you're doing this, you are plugging the entire numerator into parentheses and then dividing by the entire denominator within parentheses. And then this is going to give you about 12.11. So anytime we have natural log or log expressions and they're just involving numbers, we do actually want to estimate what is that going to give us as a decimal, okay? So this would be our final answer. So again, this one's a little bit weird just because of the x's in both sides of the equation. And so when you run into something like this, you may have to do what we ended up doing, which is distributing and then moving your x terms all to one side and then factoring out in front. Okay, so that is our last example. This is your homework for 542, so you can pull up the PDF. You have numbers 1 through 6 and then 23 through 33 odd.